Our next application brief is related to spacecraft charging on the surface of the moon. When we navigate to the moon and send people to the moon, we have to worry about dust, we have to worry about charged particles that are free floating in space and how they interact with the equipment that we're bringing up to the surface of the moon. One of the major things we have to consider is how the lower energy particles interact with the surface of our satellites, our spacesuits, and even our new infrastructure that we're building to be able to stay on the moon in the future. It's very important to do the analysis for spacecraft charging, and more specifically, surface charging, and how the electrons and protons interact with the surface, because it will lead to a risk of electrostatic discharge if we are not careful. When we look at surface charging, we have to worry about a charge balance near the surface. This is different than deep dielectric charging. At the surface, we have to handle the potential that builds up at the surface of the material with respect to the plasma environment that we're exposed to. The lunar plasma environment is very specific, and we have standards that describe how that plasma behaves in terms of energy and density. And we can also leverage the physics that we're aware of in terms of the light from the sun and how it interacts with the surface of the material. With that, we can solve for the balance of charge near the surface and assess if a dielectric material will charge differently from a conductive material. In some cases, the differential charging between the two is so high that we're going to have a ESD that will be generated. ESD stands for an electrostatic discharge, and the consequences are very drastic. We can get full damage to the component, or we can get just some RF interference with other equipment. In Ansys Charge Plus, we can solve for that balance of charge. We have an easy user interface and workflow to assign material properties, but also various space environments, depending on where you're traveling to. If you are going to the surface of the moon, you're going to have a very different environment than if you are in geosynchronous orbit. The CAD geometry that we are looking at here is that of a lunar lander. The lunar lander typically is dropped from either a shuttle or and arrives at the surface of the moon. At the surface of the moon, there are a lot of things to consider in addition to the space environment. There's also dust, there is the ground, and there are various ways to actually generate electromagnetic fields that could be consequential in terms of the ESD risk. As you can see here with Ansys Charge Plus, we're able to create a mesh with a very fine resolution and keep a lot of the components that are critical to the mission, like the antennas, the solar arrays, and various electronic boxes. When we look at the material and their properties, we can see that they're going to have a very different response for the risk of ESD and the potential differences that we can get in one environment or the other. In the Ansys Charge Plus user interface, you can load the results very efficiently and visualize those fields once you reach the steady state solution of the solver. We are using a state-of-the-art visualization tool to be able to look at the potentials at the surface, which will vary depending on the material that we're choosing, and also at the electromagnetic fields. From this surface charging simulation, you can see how critical the choice of material is to prevent the risk of ESD. The lunar environment is harsher than ever with the presence of dust that will lead to triboelectrification effects. In Ansys Charge Plus, you can model surface charging and prevent the risk of ESD.